Yes.
Okay.
Yes, we can see it. Yes.
Thank you again. So today I will be giving the presentation about probably the last work done with RAMAZ Grigolia, and it was our joint interdisciplinary project with the immunologists. And so the main objective of this collaboration is to introduce a logical system based on the properties and innate ability of biology, and to analyze the responses from relational processes when they are represented by relational systems that model such a biological system, and specifically the immune system. And finally, to give immunologists some useful tools for diagnosing the states of the immune systems based on some initial data, and to argue about and reason about these systems using the formal language of logic and mathematics. So the first steps in this direction. So Wooger in 1930s was the first one who started discussing biology with precision and reliability of reasoning. And then later in the 50s, Rashevsky and later Rosen founded relational biology and the relational theory of biological systems. Some previous work that is relevant to this talk, I divided it in two parts. So the first one is the work done in respect to modeling the immune systems. It was mainly by Dinola Grigolia and Nuno Mickiewicz. And the first attempt was in 2015 when they used the three-valued Łukasiewicz logic to model and argue and talk about this system. So apart from 0 and 1, they used the constant element of 1/2, which was interpreted as the as the neutral element or in between element, or as in between element. The next step was further extending this signature of the logic with the constants, and it came from the practical points of view. And actually, this paper from 2017, I think it was exactly the one that was presented in Tbilisi-Salerno joint workshop in 2017. We heard about this workshop from Johan and Antonio in the first session of our conference. And the further step was, of course, to consider the n-valued Łukasiewicz logic. It was the dynamic n-valued Łukasiewicz logic was used, where there was a combination of MV algebras and the combination of some regular algebras capturing some R rings with R rings with multiplications. And as about the logical and mathematical part of the relevant to this work, the main part was also done by Dinola and Grigolia. Here I give some several. Actual first one is the book, Fuzzy Logic of Quasi-Truth. It was also mentioned by Antonio in the morning session, and epistemic Łukasiewicz logic and the multimodal MV algebras have been discussed and characterized in this paper from 2022. So previous approaches had all of them had three gradations or propositions. It was true, false, or in between value. So in between, mostly it was used one half, and it was interpreted as unknown, neutral, or semi-activated, or things like that. And the common property of all those models were that if we had alpha that was that had value of in between, then by taking the alpha in three-valued case 2 times or in n-valued n times gave us false. So basically, there was 2 static values that 0 and 1, and the neutral element, depending on the operators, could have skewed in one of the directions. And the most distinction, and the novelty of this in this paper, so the new approach is to use the infinitesimals. And the notion of the infinitesimal is used to model the quasi-false, and its negation will be quasi-true, and thus we obtain 4 gradations, so not true, false in between. Here we have 4 gradations of true, quasi-true, quasi-false, and false. And it preserves the property that if alpha is quasi-true, then alpha and alpha is quasi-true, which was not the case previously. And if alpha is quasi, then alpha or alpha is quasi-false. And as the knowledge operator, we have two interpretations of this knowledge operator. So we have the full knowledge, or it can be interpreted as full activation, depending on the context. Or we have the now additional quasi-knowledge operator, which will model the partial knowledge or partial activation, or quasi-activation, as we call it. So we study, so how do we approach this system? So we study the logical system and the semantics as relational systems with applications for the immune systems. And in turn, these systems consist of special cells, which are T cells. We call them like it's sort of clever cells that clever in a sense that they may possess the knowledge about the states of the other cells, and act accordingly. So the behavior depends on the knowledge these T cells or information these T cells possess about the environment or the other cells. We have so the interpretation of the box alpha as the agent knows proposition alpha. We have box Q that the agent quasi knows proposition alpha, and we have dual operators for boxes that the agent doesn't know that proposition alpha is false, and the agent doesn't know that proposition alpha is quasi false. So a quick sum up about the MV algebra. So here at the bottom you can see the main example of the MV algebra, which is a 0-1 segment endowed with the operation of sum, restricted sum, and dual multiplication. And MV algebras are algebraic semantics of the Łukasiewicz logic. And in general, they are not semi-simple, or so their intersection of its maximal ideals is not 0. So in other words, it has a non-zero radical. And exactly these elements of non-zero radical are called infinitesimals. Why do we call them infinitesimals? Because no matter how many times we add them up to themselves, we cannot get to the 1. So there's no such n that nx will be equal to 1. And the first example of non-simple MV chain was given by Chang, and he described the MV algebra C. And this algebra has already been mentioned in Antonio's talk. He gave its representation as the lexicographic product. Here I have a more algebraic presentation, so it's still just two copies of natural numbers, one on top, reversed and on top of another. And here is the definition of and how it is a chain C that is Chang's algebra, and here is the graphical representation of it. So why this is interesting? So the algebra C is the simplest MV algebra that has infinitesimals, and all of its elements are either infinitesimals or co-infinitesimals. And if we take any non-simple MV algebra, it contains a copy of C as subalgebra, and C is generated by its radical. And if we factorize it by the radical, we get 0, 1. So up to infinitesimal elements, it's somewhat like the Boolean algebra of 0 and 1. So it is generated by an atom C. So here we have an atom that generates the whole. So we can add up all the elements. We can take negations and take the other part. So this element C generates the whole algebra C, XC, and this atom can be interpreted as a quasi-false truth value. Its negation then will be the quasi-true value, and as we already know, if x is quasi-true, then x multiplication of x n times over itself is also quasi-true, no matter what n will be. So the quasi-true values of this algebra are co-infinitesimals, quasi-false values are infinitesimals. And by the contrast, there is no notion of quasi-truth in 0, 1, satisfying the previous statement. And every algebra is generated by the infinitesimals have a special name. They are called the perfect MV algebras. They form a subcategory that is not a variety, but we consider the variety, the subvariety of MV algebras that is generated by the algebra C, and we'll denote it as MVC. And as we know, the class of perfect MV algebras is included in the variety MVC. Further, we have to add, I will skip some technical parts. I will not give the axiomatization. We add axioms and monadic operators to the MVC, thus obtaining the MMVC algebras. And plus, we have this axiom that gives us the final variety that we're interested in. It's the variety of variety MMVC of multimodal MV algebras generated by the perfect algebra C. On the logical part, we have Łukasiewicz logic with its axioms and inference rules defined in the 1930s by Łukasiewicz. We add for modal epistemic propositional calculus, we add the following scheme of axioms and the inference rules to the Łukasiewicz logic, and add one more axiom that will capture the analogical analog of the perfect, the axiom of that gives us the perfect algebras. And thus we get an model epistemic Łukasiewicz logic ELP, and we can show that VC algebras are algebraic counterparts of ELP. So if we have formula in ELP, it's a theorem if and only if it is valid in all MMVC algebras. This class of algebras is already well studied. I already mentioned several papers that gives some results about these varieties and the characteristics of these and free algebras and so on and so on. But I will mention here about unification, its unification type. So the unification type of the equational class MVC is one, or is unitary, or reformulated in for the logic, we will have that the unification type of the logic ELP is unitary. So what it means is that if we have any formula, there exists a unique to equivalence, there exists a unique substitution that will make this formula a theorem. In other words, if we have an equation that of this logic, then this equation can be solved and for each equation there exists a unique general solution. We will use it later. And also in this logic, so this logic ELP is decidable. And we'll have, and also I want to add that there's a procedure to verify if okay, yeah. The logic ELP is decidable. Okay, so how do we try to model the immune system? So we try to model it as the Kripke models. And in this case, we have the Kripke models that have the valuation in our algebra C. So what are these Kripke models? So Kripke models are the for Kripke models, civil Kripke model, we have Kripke frame and an evaluation. So Kripke frame is just a set of non-empty finite set of possible words which have binary, reflexive, and transitive relation on them. It's called the accessibility relation. And we have an evaluation on this frame such that for each propositional variable, if this evaluation is 1, then it should be 1 as well for all of its successors. And the same if the evaluation of this propositional variable is in the negation of the radical, then for all of these its successors, the evaluation should also be in the negation of the radical of C. And extending this evaluation for all the formulas of ELP, we will have that if phi is a propositional formula of LP, then this evaluation is a propositional one. And if phi is a model formula, then for time Q phi, we will have the disjunction of all the evaluations
I'm sorry,
on
I
all
couldn't
of these.
see your video. I couldn't see your desktop. I
Sorry?
think, yeah, I couldn't see your picture because it's dark.
So what is it on the screen?
Your camera, RAMAZ, to see your face, I think.
So sorry, do you see the slides?
Yes, we did. We
No.
see. But I think the question was regarding the video of yourself.
I don't have the camera on this computer, so
Okay.
sorry.
Yeah. Oh, sorry.
Please.
So you see the slides, right?
Yes.
Okay. So yeah, and if we have the box queue, then we have all the conjunction of all the evaluations of the phi's, all the phi on all of its evaluations of all of its successors. And the model formula phi is said to be modally valid when it is evaluated to 1 in all finite Kripke models, and we'll call it quasi-valid when it is evaluated to an element of negation of the radical C in all Kripke models. And we'll say that it's model 1 satisfiable when there is some Kripke model and some word W such that the evaluation is 1 in this model. And the same we can we'll say that the model quasi-satisfiable when there is some Kripke model and some word W where this evaluation is in this negation of the radical. And we can prove that any theorem of phi of the logic LP is modally valid, and also that any modally valid formula phi of the logic LP is a theorem. So we have this both ways. Now, a couple of words about the system we're trying to model. So it's no surprise there are lots of different types of cells which are involved in the immune system and its functions, and having different functions and different interactions in between them. So here is one of the examples of how such cells can interact. This is one of the models of the interactions between some of those cells. And as we already said, so the T cells are the cells that we call clever, right? So they, on one hand, they can be activated by some input signal. They also can be quasi-activated. So this will be the some difference in the notions and in the terms used in the previous papers and other approaches. And moreover, any T cell can know that some T cell is either activated, quasi-activated, or not activated, or etc. Here, this is the more simplified version of the relational correspondence between several types of the cells, so the immune system IMS is represented as a set of T cells with some actions between them. So identifying T cell with an agent or possible world and an action between T cells with a relation between agents, we can represent IMS as a C-valued descriptive Kripke frame. And in this frames, we can define the notions of the activation of and quasi-activation, but what we mean by activated, not activated, quasi-activated, and not quasi-activated, in line with the previous definitions. So we have these conditions and of T cells they can be in. Here is a simple fragment and simple example. Here we have 4 types of cells: Th1, Th2, APC, and TEF. And here is a reflexive closure of this graph that we constructed from the previous one, and here's an example of the evaluation of the one of the evaluations and one of the examples of a Kripke model in this setting. So a function ES is called an epistemic state function if for every W and W prime. If epistemic state function is evaluated to 1 on any W, then it should be evaluated to 1 in all of its successors, and the same holds for if it is evaluated to the negation of the radical, or if the valuation is at least quasi-true, then the evaluation of all of its successors should also remain quasi-true, at least quasi-true. Now, suppose we have formula phi, and we have some evaluation, and we can define function for each evaluation and each formula in such a way that it will be in a given way, and we say that the formula phi is labeled by the evaluation E if this is an epistemic function, and we will denote such kind of function by ESE phi. And the process of transformation act of one epistemic function to another epistemic function we'll call phi activation. So for a formula phi, a transferring of the epistemic state function to the one epistemic function to another epistemic function is a phi activation of points of W. Here again is a small example. If we have a different relation, different type of cells, different relations. And here we constructed the epistemic state function for the formula phi P or not P. Here's one example for this. So we defined the activation function act as a function, as functions defined on the set of all epistemic states with value in the same set. And this is the way to represent how the epistemic information changes after, say, an experiment that produces new information about the epistemic values of all the points. And to know facts about the function, this function means to know facts about the possible variations of the epistemic state of the system, and to check whether these variations can be described by formulas. And given a collection of epistemic states, finding a formula representing how to find a formula that represents such a collection. So what can be the approach, and how can we use these tools for real life situations and for in real life cases? So the first rough sketch is that suppose we experimentally establish some concrete first order sentence, say phi, valid for the current state. We can construct a propositional formula phi corresponding to phi prime, and we can ask what formulas, say psi, will be consequences of phi. So this is already a logical mathematical question. And in other words, what kind of properties can we deduce from phi? So, and more precisely is the rule psi admissible. So we will use known results from our logical systems to conclude and to speak about possible consequences in these systems of the real life examples. Another one can be like this. So suppose we have the state of the system, and this state can be represented by some formula phi. And the conditions for which this state is achieved act as a unifier of the formula phi. And the question now is, what measures do we need to take to achieve these states? And to answer this, it's like in more and we can ask this question in logical words. More precisely, what is the unifier of the phi? And again, we know that this such a unifier exists, and we can in hindsight, we can actually compute this and find this most general unifier. So this is the paper. It was published this year in the Archive for Mathematical Logic, and yeah, for now it's the last joint paper with RAMAZ Grigolia. Hopefully this will not be the first, because we still have some unpublished work, and hopefully we'll publish next year. But all the information about this talk and the results obtained in given today are given in this paper. Thank you very much for your attention.